Welcome to my presentation. First of all, I want to give thanks to the Honorable Chair, also to the professors and experts who will see this presentation. Also, I want to give thanks to the Committee of International Conferences on Digital Technology Driven Engineering 2025. My presentation title is High Performance Failure Prediction in Industrial Engines, a random forest approach with advanced feature engineering and SHAP interpretability. The authors are listed here. The contents of the presentation are introduction, methodology, model evaluation and results, feature importance, SHAP, synthetic data and model robustness, future work, conclusion. Introduction. Predictive maintenance is a proactive strategy used to predict failures in industrial engines, minimizing downtime and repair costs. Traditional PDM approaches often rely on time-based maintenance, which can be inefficient. However, there is a challenge in obtaining enough labeled data for accurate failure prediction. This research addresses the lack of labeled data by using synthetic data to train the model, providing a high-performance solution for engine failure prediction using advanced machine learning techniques such as random forest, feature engineering, and SHAP interpretability. Methodology. Data generation. Synthetic data is generated to simulate engine operating conditions, RPM, temperature, oil pressure, vibration, load, and failure probabilities. This synthetic data enables the model to be trained even when real-world data is scarce, overcoming a major limitations in PDM. Data pre-processing. The data undergoes several processing steps, KNN imputation to handle missing values, outlier detection using isolation forest, and feature scaling via robust scaler to ensure high quality input for the model. Feature engineering. Various feature engineering techniques such as creating interactive terms, polynomial features, and lag features are employed to enhance model accuracy. These methods capture complex relationships and time dependencies, improving predictions. And in the table, it is shown that RPM by temperatures, feature name, and technique interaction term. And the purpose of this is capture nonlinear interaction. And RPM, polynomial feature, and purpose is model acceleration effects. Lag RPM, the technique is lag feature, and the purpose is preserve temporal structure. And at the end, rolling vibration, the technique is rolling mean, and the purpose is smooth vibration signal detect anomaly. Here random forest is used, and a random forest model is used due to its ability to handle complex high dimensional data. It combines multiple decision trees to improve accuracy and reduce overfitting, making it ideal for failure prediction. After the methodology, we will go on to model evaluation and results. The performance matrices are shown here. The model is evaluated using accuracy, ROC, AOC, and PRAUC. High scores have been shown here, and the accuracy is 97.34%. ROC, AOC 0.9966, PRAUC 0.9970 demonstrate the model's exceptional ability to predict failure. And after many experiments and further improving the models, the results have been observed, and finally which result is found more frequently and average results are shown in the table. So the final results which have been found from the random forest model is the accuracy is overall on average accuracy is 83.33, ROC-AUC 0.92, PR-AUC 0.85. This table is showing the result after evaluating many times, after testing the many times. This is the final result, and the above description is the top results which have been found when we are evaluating the results, and the table is the final result. Feature importance: SHAP values are used to explain the model's predictions, identifying key features such as RPM, temperature and oil pressure that significantly impact the failure prediction. This enhances model transparency and trust. This is the random forest failure prediction feature importance has been shown, which features giving the impact more on the experiment and the features. It has been shown in the figure, in the diagram. Synthetic data and model robustness. A comparison between synthetic and real-world data shows that the model trained on synthetic data performs similarly to one trained on actual data, demonstrating its robustness and generalization ability. These are the figures which is showing the results and predicted value by true level. You can see the value 3000 to 220 and the 3192. So the results is significant, and the confusion matrix showing that the results are significant. And also the false means the correct, and true is the error done by the model. So the correctness is way too high comparing to the false, comparing to the errors which is mentioned here is as true. So the model is performing well. So future work, what can more we do in the future, and what can be implemented future so that the results can be more accurate, more significant and more practically usable. So the future works can be on validating the model with real world data, incorporating time series data to capture temporal dependencies, exploring more advanced models such as deep learning and XGBoost. This is important point because we can also work on deep learning to enhance the topic. And the last one, we can say implementing sensor fusion to enhance the model's predictive capabilities. And in conclusion, this study presents a high-performance machine learning framework for predicting engine failures using synthetic data. The random forest model combined with advanced feature engineering and sharp interpretability offers an effective and transparent solution. Future work will focus on validating the model in real-world conditions and enhancing its accuracy with more advanced techniques such as deep learning, such as other models, even we can use some pre-trained models, so the work can be more significant in future. So these are the references of our work. All the references are shown here. So thank you.